To divide complex numbers, we're going to follow a similar chain of thought that we did with rationalizing radical expressions. Because keep in mind, the imaginary unit is itself a radical expression. It is the square root of -1. Just like with rationalizing radical expressions, we use conjugates. In this case, we're going to use what are called complex conjugates. Again, it's the same numbers, but this time we have a real number and an imaginary number, and the opposite operation. So we're going to have a plus bi and a minus bi. The reason this works so well is because if I take two complex conjugates, such as a plus bi and a minus bi, and I multiply these together, I always get a real number product. So a times a gives me a squared. A times negative bi is negative abi. Bi times a is a positive abi, and then we have negative b squared I squared. What this does is it causes these middle terms to cancel out because these are the same terms but different signs, and we're left with a squared minus b squared I squared. Well, the I squared also turns into -1. So we have b squared times -1, which ends up becoming a squared plus b squared, where a and b are the real numbers within the complex numbers. We had a similar example earlier where we had the multiplication, and we ended up having 49, which is 7 squared. We ended up having 9 squared, or sorry, 3 squared, which was 9. And then the I squared made it a positive. And then the middle two multiplications, the negative 21i and the positive 21i, ended up canceling each other out. So we just had the a term, which was 7, the b value, which was 3. We had 7 squared plus 3 squared ends up equaling 58. And so that's how we're going to simplify and divide these complex numbers, is by multiplying by the complex conjugate of the denominator, just like with our radical expressions. So here, our denominator is 4 minus 3i, so we're going to multiply by the conjugate of 4 plus 3i. Now I'm going to do the long way to start and show the full distributive property, and then show how we can use our shortcut for the denominator. The numerator will always be a distributive property. We'll have 24 times 18i, or plus 18i, and then plus 8i, and plus 6i squared. Again, we can combine like terms here. This will give us the 26i, and plus 6i squared, since I squared equals -1, we end up with a -6. So I have 24 plus 26i minus 6, and we can combine our like terms, 18 plus 26i, that's our numerator. Then we can go ahead and do the denominator. We're going to have 4 times 4, which is 16. Then we're going to have plus 12i and a negative 12i. Again, like we see, these two values are going to cancel. And then we're going to have negative 9i squared. Of course, as I squared equals -1, which changes this to a plus 9. So we have 16 plus 9. Let's see how our shortcut could have gotten us the same value with a little bit less work. Because these are complex conjugates, we know that these are going to behave in a very specific way. We know that the product of complex conjugates is a squared plus b squared, where a is 4 and b is 3. So we have 16 plus 9. So we get the same result because we understand the pattern within the complex conjugates, giving us a denominator of 25. So here's our denominator, and we've already got our numerator, 18 plus 26i over 25. The last thing that we need to do to finish up is write it in the form a plus bi. So we need to write it as two separate fractions since we have one fraction over a common denominator. 18 over 25 plus 26 over 25i. If we could simplify the fractions, we would do so. So we'll repeat the process. Our conjugate here is 3 minus I. So we'll multiply top and bottom by 3 minus I. For the numerator, we have 12 minus 4i minus 3i plus I squared. Then the denominator, we're going to have a squared plus b squared. In this case, b is 1 because there's no coefficient in front of x. In the numerator, we can combine like terms. That gives us minus 7i. The plus I squared also becomes negative 1 over 9 plus 1. And then we can go ahead and combine these like terms, giving us 11 minus 7i over 10. And we'll write it as two separate fractions as 11 over 10 minus 7 over 10i. Last but not least, we've got 5 over 6i. So the conjugate, the complex conjugate, this is going to be negative 6i. And I'm going to show you a little shortcut after that, but just so that we can follow the same process we have before. So we multiply our numerator, we get negative 30i over negative 36i squared. I squared, of course, equals negative 1, so we have negative 30i over a positive 36. We can reduce this fraction to negative 5 over 6, and then we put the I out front, or at the end. A little bit of a shortcut. If our denominator is a monomial, it is just 6i, or any other monomial expression that is non-real. We don't need to actually multiply by the complex conjugate. We just need to multiply by I. Because if I multiply the top and the bottom of my fraction by the imaginary unit, I'm still not changing the value of the expression, but that will still help me end up getting rid of the imaginary unit in the denominator. 6i times I is 6i squared, and that leaves me with 5i over negative 6, which of course we can then simplify to negative 5/6i. So we get the same result. Go a little bit faster. If our denominator is a monomial, we don't have to use the full conjugate. We can just multiply top and bottom by I.